Imagine a dataset where every point lives in 500 dimensions. Word vectors, single-cell measurements, image features, all of them are far too high-dimensional for any human to picture. Your eyes handle 2 dimensions, maybe 3, so how do you ever see the shape of data like that? Umap is the tool that squashes those hundreds of dimensions down to a flat picture you can actually look at, while carefully preserving which points were neighbors in the original space. It has become the standard way to inspect embeddings. Let us unpack how it pulls this off. Look, Umap rests on one assumption, that the data really lives on a lower dimensional surface, a manifold tangled up inside that huge space. It recovers that surface in 2 stages, so follow them one at a time. Start with your high-dimensional points, each one a long vector of numbers. On their own, they are impossible to visualize, but UMAP assumes they are not scattered randomly. They sit on some lower dimensional manifold we are about to uncover. Next, build a graph. For every point, Umap finds its nearest neighbors in the high-dimensional space and connects them with weighted edges, stronger for closer points. This web of local connections is how UMAP captures the fine-grained structure of the original data. Then optimize a layout. Umap drops all the points into a flat, 2-dimensional space and nudges them around until their low-dimensional graph matches the high-dimensional one as closely as possible. Neighbors stay close, and unrelated points drift apart. Finally, read the clusters straight off the map. Points that were genuinely similar now sit together in tight groups you can see at a glance. So the plot becomes a faithful, browsable summary of a space you could never have pictured directly. Word vectors, single-cell profiles, image features, all of them turn into a landscape you can explore. So why bother with all this machinery? Here is the before and after side by side. Raw data in hundreds of dimensions is simply impossible to see. You can compute with it and train models on it, but you cannot look at it, so patterns, clusters, and outliers stay completely hidden. Staring at a giant table of numbers tells you almost nothing about the structure inside. Umap turns that same data into a 2-dimensional map that keeps the neighborhoods intact. Points that were close in the original space stay close in the picture, so clusters and relationships you could never have spotted suddenly jump right out. It is a qualitative map you can actually explore with your eyes. Strip it down and 3 ideas make UMAP what it is. It builds a nearest neighbor graph of the data. By connecting each point to its closest neighbors in the original high-dimensional space, Umap captures the local structure that everything else is built on. It optimizes a low-dimensional layout to match that graph. Umap arranges the points in 2 or 3 dimensions so their neighbor relationships line up with the original, turning an abstract manifold into a picture you can read. It runs much faster than its older rival t-SNE and tends to preserve more of the global structure, so the distances between clusters carry real meaning, not just the local neighborhoods. 2 knobs, the number of neighbors and the minimum distance, trade fine detail against the big picture. Alright, let us lock in the essentials. Umap is a dimensionality reduction technique that squashes high-dimensional data down to 2 or 3 dimensions so you can finally visualize it. It works in 2 stages, first building a nearest neighbor graph in the original space, then optimizing a low-dimensional layout that preserves it. It runs far faster than t-SNE, scales to millions of points, and keeps more of the global structure between clusters intact than its older rival does. Just remember the caveats: the axes mean nothing and exact distances should not be overinterpreted, since it is a qualitative map, not a metric space. If this style of untangling machine learning works for you, a whole shelf of these explainers is waiting for you at standarity.com. Come take a look.